Hi everyone, welcome to Chapter 7, Carbohydrates and Glycobiology. This chapter introduces the major classes of carbohydrates and glycoconjugates and provides a few examples of their many structural and functional roles. In this part, we will examine monosaccharides. These are the learning goals for this chapter. First, we will understand structures and names of monosaccharides. Next, we will look at open chain and closed chain or ring forms of monosaccharides. Structures and properties of disaccharides. We'll look at biological function of polysaccharides. And finally, biological functions of glycoconjugates. So, what are carbohydrates? In a chemist's term, carbohydrates are polyhydroxyaldehydes or ketones. Not all, but many have this molecular formula CnH2ON as shown here. Some carbohydrates also contain nitrogen. Carbohydrates are produced from carbon dioxide and water via photosynthesis in plants. Carbohydrates range from as small as glyceraldehyde, which has a molecular weight of 90 grams per mole, to as large as amylopectin, which is a polymer, which has a molecular weight of 200 million grams per mole. They fulfill a variety of functions, which includes these, but are not limited to. For example, energy source and energy storage. Polysaccharides like amylopectin are especially used for energy storage. Structural components of cell walls and exoskeletons. For example, the exoskeletons of insects and also peptidoglycans in bacterial cell walls are made up of polysaccharides, which are nothing but carbohydrates. Informational molecules in cell signaling. Some of these are monosaccharides and disaccharides, and some polysaccharides on the outside of the cells act as signaling molecules. They can be covalently linked with proteins to form glycoproteins and proteoglycans. We'll talk about this later. Carbohydrates, as I said, are polyhydroxyaldehydes or polyhydroxyketones, as shown here. These are polyhydroxy with an aldehyde functional group. A typical example is D-glucose. Fructose is a polyhydroxy compound with a ketone functional group. Both these compounds are carbohydrates. The basic unit in a sugar molecule is called as a saccharide. Monosaccharide is a single sugar unit. Disaccharide has two sugar units covalently bound. Oligosaccharide is a short chain of sugars, which consists of multiple monosaccharides covalently attached to themselves. Polysaccharide is an oligosaccharide that has greater than 20 sugar units. A monosaccharide consists of a single sugar unit. The most common biological monosaccharide is D-glucose. The structure of D-glucose is shown here. It has 6 carbons, 1, 2, 3, 4, 5, 6. Most biologically relevant monosaccharides have 3 to 6 carbons. Greater than 4 carbons can readily form cyclic structures. We'll talk about this in a bit. Each monosaccharide in its linear form contains one carbonyl or C double bond O group. The rest of the carbons are bound to hydroxy groups. For example, in glucose, this carbon, which is carbon 1, is an aldehyde, has a carbonyl. All the other carbons have a hydroxy group attached, carbon 2, 3, 4, 5, and 6. On the other hand, D-fructose, which is a keto hexose, has a ketone group on carbon 2. All the other carbons, including 1, 3, 4, 5, and 6, have hydroxy substituents attached to them. Now, these are called as Fischer projections. And in the Fischer projections, they always put C double bond O towards the top. So if it is an aldohexose or D-glucose, the first carbon is an aldehyde, which is a C double bond O. In D-fructose, the second carbon is C double bond O. Naming monomeric sugars. All mono and disaccharide names end in OSE or OS. Typical naming will include the number of carbon atoms in the sugar molecule. For example, if you have 3 carbons in a monosaccharide, it is called as a triose. 4 carbon, tetrose. 5, pentose. 6, hexose. Rare examples of heptose, octose, and nonose also exist in biology. Carbohydrates, especially simple ones, will often have common names. Let us consider the difference between aldose and a ketose. Monosaccharides, as I said, can be further divided into aldoses and ketoses. If the first or the last carbon in the chain is a carbonyl, then it's an aldose. And if it's a Fischer projection, it's always the first carbon. If the first carbon is a carbonyl or an aldehyde, then it is an aldose. Ketoses have the carbonyl anywhere else other than the final position or the first position, as shown here. In fructose, the carbonyl is in the second position. Sugars are chiral because they have non-superimposable mirror images. For example, if you consider the Fischer projection of a 3-membered sugar like glyceraldehyde, glyceraldehyde has 2 different stereoisomers, D-glyceraldehyde and L-glyceraldehyde. Chirality adds more structural diversity and another level of nomenclature. For example, D and L. Most carbons in a sugar are chiral. Aldoses naturally have on average more chiral centers than ketoses. As I said, glyceraldehyde is a simple 3-carbon sugar. The central carbon is chiral because it has 4 different substituents attached to it. This is the standard by which the configurational stereochemistry of D and L are set for other sugars, which means that based on whether the hydroxy group is on the right side of the carbon or not, it is called as a D-glyceraldehyde. If this hydroxy group is on the left side, then it is L-glyceraldehyde. This is the standard by which the stereochemical configurations are set for other sugars. That's what this statement means. Shown here with wedges is a perspective formula. Now, with the vast number of multi-carbon sugars, we need a simple way of representing them. We cannot just go around drawing wedges between bonds, right? So Fisher projections are used for this purpose. They use D and L representations of glyceraldehyde to name sugars. Now, the nomenclature is the same, and the way glyceraldehyde, D-glyceraldehyde, and L-glyceraldehyde is defined is also the same as I explained in the previous slide. D-glyceraldehyde is called as D-glyceraldehyde because the OH group is on the right side of the carbon. How would you draw a Fisher projection? A Fisher projection is used because it's simpler than using a perspective formulae. Chiral carbohydrates are commonly represented by Fisher projections. The horizontal lines that are shown here are pointing towards you. Now you can relate it to the perspective formulae where you have this bond facing up. These are bold bonds. Horizontal means coming towards you, and vertical bonds are projecting away from you, as shown by these wedges. Sugar chirality is defined by the nomenclature of D-glyceraldehyde and L-glyceraldehyde. And this is again re-emphasizing and reiterating the same fact that I told you a couple of slides back. Compare the stereochemistry of the chiral center most distant from the carbonyl to D and L-glyceraldehyde. D sugars will be drawn with the hydroxyl on the right. And the stereochemistry is for the chiral center most distant from the aldehyde. Whereas L sugars will have the reference hydroxy on the left. Let's look at an example. All right, here is an aldose. Which one is D and which one is L? As per definition, the chiral center, that is the most distant from the carbonyl. Is this the most distant? No. Is this the most distant? No. This is the most distant chiral carbon, right? Because how many chiral carbons are there? Is this chiral? No, it is not. Is this? Yes, it is chiral because it has 1, 2, 3, 4. 4 different substituents attached to it. Is this chiral? Yes, because it has 1, 2, 3, 4. 4 different substituents attached to it. Is this chiral? Yes, because it has 1, 2, 3, and 4 different substituents attached to it. Is this chiral? No, it is not, because it doesn't have 4 different substituents attached to it. Now, what is the stereochemistry? Is it D or L? Now, because the hydroxy is on the right and right-hand side attached to the carbon, that is chiral, which is most distant from the carbonyl carbon, this is D. This one is L. Besides enantiomers, we have another term that we call to differentiate various different sugars, and that is epimers. Epimers are 2 sugars that differ only in the configuration around 1 carbon atom. For example, if you look at glucose, glucose has 6 carbons starting from the aldehyde, 1, 2, 3, 4, 5, 6. Now, as you can see, the hydroxy group on the chiral carbon that is most distant from the aldehyde is on the right, and hence it's called as a D-glucose. Now, the differences in this hydroxy group orientation is that C3 has a hydroxy on the left. Now let us consider 2 other sugars like mannose. D-mannose, it's D because again, carbon 5 has a hydroxy on the right. Whereas carbon 2 has a hydroxy on the left as compared to D-glucose. D-galactose, again D because hydroxy on the right on carbon 5, whereas hydroxy on the left on carbon 4. Hence, D-mannose is an epimer of D-glucose. It's an epimer at C2. And D-galactose is an epimer of D-glucose at C4. Let us look at some of the 4, 5, and 6 carbon D-aldoses. The 4 carbon aldoses, there are 2 of them, D-erythrose and D-threose. Remember, these are D-aldoses. 5 carbon D-aldoses, there are 4 of them, ribose, D-ribose, D-arabinose, D-xylose, and D-lysose. And one of the most common things among all these sugars is that they are D sugars, which means the carbon that is distant from the aldehyde has a hydroxy on the right. The differences is on the arrangement of the hydroxyl on other chiral carbons. But about 6 carbon aldoses, there's 1, 2, 3, 4, 5, 6, 7, 8 of them. And I'm not going to read all of them. Some of the important ones are D-glucose, D-mannose, and D-galactose. And as you can see, as you can go from D-allose to D-talose, you can see that the hydroxy group on the chiral carbons, other than carbon 5, it is 4, 3, and 2, are on right in D-allose, whereas on D-talose, the hydroxys are on left on 2, 3, and 4 carbons. So the different combinations gave rise to different sugars. These are examples of ketoses. 3 carbon, 4 carbon, 5 carbon, or 6 carbon ketoses. And some of the most important ones are ribulose, xylulose, and fructose. There are also all the other sugars available and are physiologically relevant as well. Here is an important concept. Sugars are also cyclic. Most common 5 carbon and 6 carbon sugars adopt a cyclic structure in solution, as shown here. D-glucose in its linear form looks like this. It's a Fischer projection. And when it gets cyclized, it either forms alpha D-glucose or beta D-glucose. I'll explain to you in a little bit as to how this forms. This occurs most commonly via the reaction of the alcohol on C5 with aldehydes, aldoses, or ketoses on the carbonyl carbon. So when I say carbon 5, so the hydroxy, this hydroxy attacks the carbonyl carbon, as shown here. And this results in a cyclic form, either a beta alpha D-glucose or a beta D-glucose. The cyclization results in hemiacetals or hemiketals. So what are hemiacetals and hemiketals? Okay, let's look at 2 different structures, aldehydes and ketones. The carbons, the carbonyl carbon in aldehyde and ketone is electrophilic. Remember, I told you about this. A carbonyl carbon, as shown here, it's polarized. So this is delta plus and this is usually delta minus because of electronegativity of the oxygen. Now, because of that, nucleophiles, like alcohol, can attack that carbonyl carbon. Alcohols can attack the carbonyl carbon. So, or alcohols, like this, can attack the carbonyl carbon. And this results in the formation of a hemiacetal if an alcohol attacks an aldehyde, or hemiketal if an alcohol attacks a ketone. And hemiacetal or hemiketal can then be converted to acetal. if they further undergo attack by alcohols. So here is how cyclization of D-glucose happens. If you consider a linear or a Fisher projection of glucose, the hydroxy that is on carbon 5 attacks the carbonyl carbon, which is the aldehyde on carbon 1. Now, this structure is shown in a different way. So the linear form is represented in a different way in this structure, and what is shown here is the same, hydroxy from carbon 5, as you can see. Once this happens, there are two fates. The newly formed alcohol can either face down or it can face up. If it's up, it is called as beta D-glucopyranose, and if it is down, it is called as alpha D-glucopyranose. And this animation that is running here explains how this happens. Pentoses and hexoses readily undergo intramolecular cyclization, as shown here. The former carbonyl carbon, which is the aldehyde, the first carbon, becomes a new chiral center, as you can see. If the hydroxy is down, it's alpha D-glucopyranose, and if it's up, it's beta D. And this new chiral center is called as the anomeric carbon. This carbon 1 in the cyclic structure is called as the anomeric carbon. Another word for you to remember. The former carbonyl carbon becomes a hydroxyl group. The position of this group determines if the anomer is alpha or beta. Now, if the anomeric hydroxy group is on the opposite side of the ring as CH2OH moiety, the configuration is alpha. This is functionally equivalent to anomeric hydroxy cis to the reacting OH group, best visualized in the Fisher projection. So the easiest way to remember is this. If you now consider the stereochemistry of the CH2OH, it's up. If OH is on the opposite side or the trans side, then it's alpha D-glucopyranose. If the hydroxyl group, this hydroxyl, is on the same side or the cis side, then the configuration is beta. That's all it matters. You may have realized by now that cyclization of sugar monomers introduces another source of variability. Monosaccharides that differ only in the stereochemistry around anomeric carbon, as hemiacetals or hemiketals, are called as anomers. Remember, sugars are hemiacetals and hemiketals. They are not acetals and ketals. They are hemiacetals and hemiketals, and when they differ in their arrangement on anomeric carbons, they are called anomers. Specifically, anomers will have either alpha or beta in their name. So anomers are these 5-membered or 6-membered sugars are called as furanoses and pyranoses. Aldohexoses can form 5 or 6-membered rings. 5-membered rings are called as furanoses, named after their similarity to furan. 6-membered rings are pyranoses, named after the similarity to pyran. So again, additional naming that needs to be remembered. There are two different ways of drawing the cyclic form of monosaccharides. The first perspective is called as Haworth perspective formulae. Haworth perspectives depict cyclic sugars. Line drawn up from the carbon indicate the hydrogen or hydroxy is above the plane of the ring. For example, in case of alpha D glucopyranose, if you look at the anomeric carbon, the hydroxy is below the plane, whereas hydrogen is above the plane. Compare that to beta D glucopyranose, the anomeric hydroxy is above the plane. That's the only difference between these two 6-membered sugars. If you were to look at the 5-membered sugars, you can see alpha D fructofuranose is when the CH2OH is above the plane, and for the beta, the CH2OH is below the plane. Ring structures of monosaccharides in solution are not planar. As you can see here in Haworth projection, this ring is not planar, and this can adopt a chair conformation or a boat conformation as shown here. Most monosaccharides form chair structures. Which of the two chair is predominantly formed depends on the steric hindrance of the groups on the axial or the equatorial positions. Interconversion of beta D-glucopyranose to alpha D-glucopyranose can happen in solution. This process is called as mutarotation, and this involves bond breaking. And in this case, beta D-glucopyranose opens up, forms the linear chain, and then it's cyclized again to form alpha D-glucopyranose. This conformational change, configurational change, can happen in solution. While there is only one alpha D-glucopyranose form that is shown here, two possible chair forms are possible for beta D-glucopyranose. And these two forms are not readily interconvertible because there is about 46 kilojoules of energy that is required to convert one form to another. On the other hand, a beta D-glucopyranose configuration is preferred over alpha. Carbohydrates in solution reach equilibrium. The stability of each structural variation of a given sugar molecule determines its equilibrium population. What does it mean? A solution of glucose will reach an equilibrium in such a way that about 36% is alpha D-glucopyranose and about 64% is beta D-glucopyranose. There is a very trace amount of linear and very trace amount of glucofuranose, which is this 5-membered ring that is present in a solution of glucose at equilibrium. Ring form exists in equilibrium with the open chain form, as I said before. All monosaccharides are thus reducing sugars. Aldehydes can reduce copper 2+ to copper+, and this is done using Fehling test. Fehling's solution, if you add aldehyde to Fehling's solution, what happens is the copper 2+ in the solution turns to copper+, and there is a significant color change, as you can see, upon heating. This confirms that there is aldehyde, and hence monosaccharides can be confirmed using Fehling's test. Aldehydes can reduce silver+ to silver 0, which is in Tollens test. This allows detection of reducing sugars such as glucose. Remember, this is important. Glucose is a monosaccharide, and monosaccharides have aldehydes because the ring conformation can also become a linear conformation. And aldehydes, because of the presence of aldehydes, monosaccharides are reducing sugars because they reduce copper 2+ to copper+ or silver+ to silver 0. The most common class of biological monosaccharides are the hexoses. Hexoses are often substituted at one or more of the carbon atoms. Deoxy sugars are the most common substituted groups. One hydroxyl is converted to a hydrogen. So what are deoxy sugars? For example, ribose versus deoxyribose. 2-deoxyribose is a part of what we call as DNA, or deoxyribonucleic acid, whereas ribose is a part of RNA, or ribonucleic acids. Shown here is some of the important hexose derivatives, and these are all monosaccharides. Part of glucose family, glucose itself, beta-D-glucose, beta-D-glucose 6-phosphate. As you can see, phosphate is attached to 6-carbon and hence beta-D-glucose 6-phosphate. Now, replacing hydroxy on the 3 substitute, or the 2-carbon, to an amine can form beta-D-glucosamine. And if you acetylate that amine, it forms N-acetyl beta-D-glucosamine. One can also form muramic acid by substituting one of the hydroxy, that is the hydroxy at the 3-carbon of glucose, by using this substituent to form a muramic acid. And N-acetyl muramic acid is when you have that substituent and the amine that is acetylated, and hence N-acetyl. Similarly, galactose can be converted to galactosamine, or mannose can be converted to manosamine. Deoxy sugars are also present in 6-membered sugars like fucose and rhamnose. Acidic sugars such as sialic acids are also present in our body. For example, N-acetyl neuraminic acid is a classic sialic acid.